Well, good morning again. You ready to look at our colligative properties in more depth? We did the intro to it. We looked at, we're going to do vapor pressure lowering, boiling point elevation, freezing point depression, osmosis/osmotic pressure. So let's start with vapor pressure lowering, because I think we need to do this one before we do the other ones. All right, this will help you. Hopefully this will help you understand several of the other ones. All right, the answer is obviously stated in the title here. When you have a pure solvent, whether it's water, ammonia, methanol, ethanol, doesn't matter, at some temperature, right? It's going to have a particular vapor pressure. And we looked at, as you increase the temperature, there's more in the vapor phase, vapor pressure goes up. So let's just say we're at some constant temperature throughout this whole video, okay? So room temperature, whatever it is. That will have some value of vapor pressure, right? We can look that up in a table, right? So it's the vapor pressure for a pure solvent at some temperature. But if I now add a solute, right? So say I have some water and I sprinkle some solute in there, whatever that is. Could be mix it with another liquid, dissolve some ionic compound in there, dissolve some sugar in there. Doesn't matter. Remember, it doesn't matter the identity. We do have to account for electrolytes, though. So sodium chloride splitting up into two particles when you think it might be one, right? Exactly. The vapor pressure of the solvent, right, above the solution will be lower than the vapor pressure above its pure solvent, all right? That's the essence of it. So the vapor pressure goes down. I'm going to show you Raoult's law here. I'm going to show you a couple versions of Raoult's law. So Raoult's law by F.M. Raoult in the 1880s said, hey, did some studies. What's the vapor pressure of the solvent above the solution? And he found that was the mole fraction of the solvent times its pure vapor pressure, right? If it's a pure liquid by itself, we're assuming it's a liquid, okay? So since mole fraction has to be less than 1, that means the vapor pressure above the solution of the solvent has to be less than the pure solvent by itself, right? Because that's going to be less than 1. The sum of all the mole fractions equals 1. So it makes sense mathematically, and that's why we introduced mole fraction in one of the earlier videos on concentration. We'll get to molality in a little bit for freezing point depression and boiling point elevation. But we can think of this as maybe you've got a solvent and then you put in some non-volatile solute that doesn't, add to the vapor pressure. But we could also look at this if you mix a couple of volatile liquids as well. Instead of calling this the solvent, you could just say species A or species B. So we could just as easily say P sub B, right? If it's another liquid and they're both mixed together and both vaporized, they're both going to contribute to the vapor pressure above the solution, but you could do component A or component B. So I could just as easily put B here, would be the mole fraction of species B times the pure vapor pressure of species B. Rather than solvent solute, you could say species A, species B. Right? Different ways to look at it. Let's look at the different forms of this, and then we'll qualitatively go, well, why is the vapor pressure going down? And then we'll do some problems with it. Here we go. Another way not as common, but another way you'll see some people look at this is in terms of the title, vapor pressure lowering. So the way we looked at the Raoult's law, the most common way, right? It's just the vapor pressure of species A, or the solvent is equal to the mole fraction of species A, or the solvent times its pure vapor pressure. Well, if you want to look at it technically as vapor pressure lowering, how much does the vapor pressure go down? You can easily derive that. I'm going to leave that up to you for if you're bored on a Saturday morning or something like that. If you take Raoult's law originally, right, and realize if you have two species, right, the solvent, let's just call the solvent A, and the solute B, and for all intents and purposes, let's just say solute B is non-volatile in this scenario. Well, we know that the sum of the mole fractions must equal 1. If we had a third species, obviously, it would complicate it a little more. So can't we do just an algebraic substitution? Wouldn't the mole fraction of species A, the solvent, just be 1 minus the mole fraction of species B, the solute in this case? Okay, well, couldn't we just plug in 1 minus the mole fraction of species B in for the mole fraction of A? And if you do that, do some algebraic manipulation, so much fun! You'll end up with the actual vapor pressure lowering, right? So the pure vapor pressure minus the vapor pressure above the solution. That's how much it goes down, right? That's an equation for the vapor pressure lowering, would equal the mole fraction of the solute, species B, times the pure vapor pressure of the solvent, or species A. And remember, for that, you got to count if it's a strong electrolyte like a soluble ionic compound or something like that. You got to worry about Van Hoff factor and whatnot, okay, when you're calculating mole fractions. So that's just a second way. I don't see that nearly as often, but if you actually need to solve for the vapor pressure lowering, how much did it go down, you're perfectly fine. I think an easier way is just to use Raoult's law. If you're given the pure vapor pressure, just use Raoult's law to calculate the pressure above the solution and just subtract those two, right? I think it's a little easier. One more way I want to look at this is if you add a solute that's volatile, or if you just think of having a mixture of two liquids, like an ideal mixture of two volatile liquids, they're both going to contribute to the vapor pressure above the solution. But we can determine each one's individual contribution and just add those together. Doesn't that sound like something Dalton talked about? Oh, let's look at this on the next board. All right, here's something that we will be running into, where we have a mixture, an ideal solution, right, of two volatile liquids, i.e., this solute is a liquid and it's volatile. All right, so both the solvent and the solute, although a lot of times if you have a 50-50 mixture, it's hard to tell which is which, right? We can just say a mixture of two volatile liquids. We can apply Raoult's law equally to both of them, right? But the total pressure above the solution, remember Dalton's law of partial pressures? Dalton's law of partial pressures? That's just the partial pressure of species A plus the partial pressure of species B, if we only have two components. If we had three components, we'd have to add plus PC, etc. Right? It's PC. But both contribute to the total pressure via Dalton's law of partial pressures. But from Raoult's law, the vapor pressure of species A above the solution is just the mole fraction of that species times its pure vapor pressure. And the vapor pressure of species B above the solution is the mole fraction of species B times its pure vapor pressure, right? And if we had species C, we could continue on down the road. So very simple to do. So we can easily calculate the total pressure above a solution, an ideal solution, right? If we know the pure vapor pressures of both species. Because once we know the mole fraction of one, I could give you masses of both, or maybe volumes and densities. You could calculate the moles of each, add them together if one of them, and if this is a volatile liquid, it's not going to be an electrolyte, so the Van Hoff factor is 1, so you don't have to worry about it, right? But if we added a solute that's non-volatile, right? If it's non-volatile, but the pure vapor pressure would be 0, right? So this whole term would go to 0. This would be 0. And you get PA equals the mole fraction A times the initial pure, that little knot symbol means the pure vapor pressure of the solvent. So if this is a non-volatile species, that goes to 0, this goes to 0, and this just collapses into the original Raoult's law that we gave. Yay! Let's look at it qualitatively, why the vapor pressure lowers. I'm going to give you a real simplistic look at it, and hopefully it makes sense to you. And then we'll do some calculations. We'll do like a mixture of two volatile liquids, calculate the partial pressures of each, add them together, right? And this could actually lead to knowing the composition of the ideal solution, right? The mole fractions of A and B. We'll simplify, just say we have two species. We could actually, from that, calculate the composition of the vapor above the solution in terms of mole fractions of A and B. And we're going to see that they're not going to be the same. The composition of the solution will not be the same as the vapor above it. Think about why. Again, oversimplification, but let's just see if you can envision this from a molecular point of view. Let's take case A, case B. Case A is the pure solvent. Let's call that species A. Case B is the solution where we've added some solute. I'll make these little red particles. Sprinkle them in. Whether those are volatile or non-volatile isn't critical at this point. So let's just make the assumption these are non-volatile. Right? And then we can talk about if they are volatile. Well, let's say we've got a sealed container here, and we're going to have some of the pure solvent vaporize, and you'll have particles up in the vapor phase. And some will move and strike, moving around, bing, 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 bing. kinetic molecular theory, and they'll strike the surface and go back into the solvent, the pure solvent, and will form an equilibrium, right? So the red arrows is vaporization, green arrows is condensation. If those are equal, we're at equilibrium at some temperature, and that's the total number of gas particles in the gas phase. We talked about this when we did vapor pressure, right? Well, the vapor pressure, what we've been calling it, would just be the pressure of species A. In this case, it would be the pure solvent, P naught. So in this case, PA is P naught A. Right? The vapor pressure is that of the pure solvent, which we call VP. Obviously, we know when we add a solute, it's going to drop. The vapor pressure of A above the solution is going to be lower than the pure solvent by the mole fraction. Okay? So the lower the mole fraction of it, the less the vapor pressure. Does that make sense? Let's take a look at it. Let's say we've got our solution A plus B, and I just made B the solute, the little red dots. Would it make sense that if we're trying to vaporize, right, we're trying to head out of solution, there's nothing to impede any of the particle, the molecules of A on the surface and the pure solvent, there's nothing impeding them. They're free to vaporize at any part of the surface area there, right? But here, do you see these little red dots there? There's going to be some solute particles on the surface. Whether they're volatile or non-volatile doesn't matter. But they're physically not stopping, but physically making it harder for the solvent to vaporize because there's less space on the surface. Remember, you only get vaporization from the surface. So since there's fewer particles of A along the surface because we have some particles of B on there, there's going to be fewer of them vaporizing. Does that make sense? Kind of an oversimplified way of doing it. I picture that, the solute B, I love football. The solute, these are like offensive linemen, right? You got the offensive linemen lined up there, so it's harder to get through, right? So you're going to have fewer of the blue dots. So these blue dots are just particles or molecules of the solvent species A in the gas phase. So there's going to be fewer of them here just because it's harder to get out of solution because of the presence of the solute. Now, if that was a volatile species B, then you'd have particles of B up here, particles of B there, and the whole scenario. But they're still going to be impeding each other from getting out versus if they were both pure. Make sense? Let's do some math. Actually, the math is pretty straightforward, right? I mean, Raoult's law is pretty straightforward, pretty easy to do. I mean, I can make it hard to calculate the mole fraction because sometimes you'll get problems like in the homework. Here's the mole fraction. It's of A is 0.71. Okay, that was easy. Either look up or give you the pure vapor pressure and just multiply them. It's a piece of cake, right? And nothing here is going to be exact. Mole fractions are not exact unless it's a theoretically defined solution. The pure vapor pressures are measured in an experiment. That's not exact. And since you have two non-exact numbers, right, with some uncertainty, you'll have uncertainty. So make sure you track the significant digits there. But watch out. Mole fractions sometimes, they will come from addition. So you're limited by largest absolute uncertainty, aka fewest decimal places. But here we're multiplying, so we're limited by fewest sig figs. So there might be multiple steps depending on the information you're provided with. Are you given the mole fraction directly, or are you given masses or volumes, densities, and you got to calculate mole fractions? We're going to break this one down into like bite-sized chunks. I want my baby back ribs. All right, here we go. Here's some information for you, and if you're in lab, you could look this up. On homework, you could look this up. Okay, on a quiz or exam, I'd have to provide you this information. Let's say we're at 25 degrees Celsius, because vapor pressures depend on temperature. Let's say we have pure hexane, and that has a vapor pressure of 149.1 millimeters mercury, aka torr, at 25 degrees Celsius. And pure pentane has a vapor pressure of 508.5 millimeters mercury. Right? So information that does not necessarily have to be included in the problem if you have a handbook of chemistry and physics or some way of looking that information up. Good. Now let's make a solution. Okay, so here we are, part A. What are the partial pressures of both species? Because these are both volatile. Both hexane and pentane are volatile hydrocarbon liquids. Right? What are the partial pressures of both species above a solution when you mix 35.8 milliliters of hexane? Density is 0.66 grams per milliliter. Only 2 sig figs, so rough approximate. And we got 6.573 grams of pentane. Right? So take 35.8 milliliters of hexane, mix it up with 6.573 grams of pentane. Obviously, this one I'm giving you a volume and a density. This one I'm giving you a mass, so I can hit you with a curveball and a fastball at the same time. So remember, we're dealing with a mixture, and we're going to be assuming this is an ideal mixture. So let's take a look. So first thing, we need to know what are the identities of the formulas of pentane and hexane. We don't really need it for hexane, but we need it for pentane because we need the molar mass to get from grams to moles. So let's write these down. Ready? So pentane, I would assume you know these, right? So hexane, pent is 5, like the pentagon or a pentagram. Hex is 6. I'll put the hex on you. All right, so what is it? Cn for hydrocarbon, CnH2n plus 2. So this would be 5 carbons. So C5, 2 times 5 is 10 plus 2 is 12. C5H12. Hexane is 6, so there's 6 carbons. 2 times 6 is 12 plus 2 is 14. So that's the first thing we need, is what are their identities. And when we mix these, they're almost the same size. They're both nonpolar, only London dispersion forces. So they're going to pretty much sort of think they're the same as each other. So I would make the assumption this is going to be ideal. Now, obviously, if we're going to do any problem using Raoult's law, we have to assume it's an ideal solution. So let's call this an ideal solution. And you could just do, a lot of you could just do all this in your head, right? You don't have to write all this stuff down. So what we need to do is, the first step before we can apply Raoult's law is figure out the mole fraction of each. Right? So let's write this down. So determine moles of each and the mole fraction of A and the mole fraction of B. And you could call A pentane or you could call A hexane. It doesn't matter. You'll get the same answer. So we got to figure out the moles of each, add them together, get the total moles, and then get the mole fractions. Now these are both non-electrolytes, so we don't have to worry about the Van Hoff factor. Van Hoff factor is 1 for each. Whew, we're good with that. So go ahead and do that for me real quick, because I'm out of room. I'll write it up on the next board. Let's see if we get the same thing. Figure out the moles of pentane from the information provided. Right, mass, so get the molar mass, convert grams to moles. Get the moles of hexane, so take the volume and the density to get to grams, and then the molar mass to get from grams to moles. So I guess we did need the identity of both. And then you got the moles of each, add them together, get the total moles, and then just take the ratio to get the mole fractions. Let's see what you get. All right, a lot of stuff on this board, and we haven't got to the answer yet. So this is just figuring out the mole fraction of the two components. Right? If there's 3 components, it'd be even worse. So this would be really nice on an exam. If I just gave you the mole fraction, you could skip all of this, all right? Which is probably more likely because of the time limitations, because I already know you can do all this stuff. All right, let's take, it doesn't matter which one you start with. I started with pentane, C5H12. We were given 6.573 grams of pentane. So I took my trusty dusty periodic table with my carbon as 12.011. And my hydrogen is 1.00794, James Bond of elements. So it takes 12.011 times 5 plus 1.00794 times 12, limited by the 3 decimal places of carbon, depending which periodic table you use. If you're in my class, use my periodic table, and you'll get the same answers I do. So I got 72.15028 grams of pentane per mole of pentane, limited to 3 decimal places. So that gives us 4 sig figs in the mass, 5 sig figs in, 5 sig figs in the molar mass. So we're limited to 4 sig figs in our moles of pentane. So I get 0.0911015 moles of pentane, good to 4 decimal places. I'm not 4, it's 4 significant figures. We're doing a division there, right? So let's do the same thing for hexane, C6H14. You were given a volume this time, 35.8 milliliters. Let's use the density to convert the milliliters to grams. And then once we have the grams, we can take the molar mass. So take 12.011 times 6 plus 1.00794 times 14, limited to the 3 decimal places of the carbon. I get 86.17716 grams per mole. Grams cancel out just like they do here. And you're left with moles of hexane. So I get to, the density is going to limit us to 2 sig figs there. So we get 0.2741 moles of hexane, good to 2 significant figures. Now we need the total moles, right? To get the mole fraction, it's part over whole, right? So let's take the moles of pentane plus the moles of hexane, add those together. I got 5 decimal places in my pentane, 2 decimal places in my hexane, so I'm limited by the largest absolute uncertainty, which is the hundredths place there, 2 decimals. So the total moles of both components is 0.3652 moles total. I'm not going to round anything because I'm only going to round what I was asked for, which is the partial pressures of each component, the hexane and the pentane, above the solution. Now we can do mole fractions. So let's take the mole fraction of pentane. You could do hexane, whatever. So take the moles of the pentane, 0.0911015, divided by the total moles, which was 0.3652. And since we're doing a division, we're limited by fewest sig figs. I got 4 sig figs in my moles of pentane, 2 sig figs in my total moles, so I'm limited to 2 sig figs. So I get a mole fraction of 0.2494, good, and that's unitless, and that's good to 2 significant figures, and that's the mole fraction of pentane. Now you could do the same thing for hexane, but remember there's only 2 components, so the mole fraction of hexane plus the mole fraction of pentane should equal 1. Therefore, the mole fraction of hexane is just 1 minus the mole fraction of the other species, the pentane. Yay! Saves you from going through all that again. Yeah, saves you about 4.5 seconds. So 1 minus 0.2494, which is the mole fraction of the pentane. Let's see, that one's exact, because by definition, so we're limited to 2 decimal places. So I get a mole fraction of hexane of 0.7506. Now that we have the mole fractions, we can use Raoult's law on both species to calculate the vapor pressure above the solution of each species. Now remember, these are both non-electrolytes, so I didn't have to worry about them splitting into multiple things if I was doing moles. If this had been sodium chloride, right, with the mass here, now I could get moles of that. Then I'd have to get the moles of the sodium ions and the moles of the chloride ions, or just take that and times it by the Van Hoff factor of 2. See how that works out there? Assuming no ion pairing and all that kind of stuff in solution. So we got all mole fractions. Let's get our, let's use Raoult's law on the next board to get the vapor pressure of hexane and pentane above this solution. Go for it. Did you properly apply your Raoult's law? Right, and these are both volatile species, so we can apply Raoult's law for both species. And you could have done A, B, B, B if you had assigned those. If you don't want to keep writing the C6H14s, you could just say, hey, A equals pentane, B equals hexane. Or you could just put, PENT hex there. As long as it's labeled clearly, I'm cool with that, right? So the pressure of the pentane above the mixture, the solution, is equal to the mole fraction of the pentane times its pure vapor pressure, which I provided for you, right? So let's take the point, you always use the non-rounded values, right? Take the 0.2494, that was the mole fraction of the pentane in the solution, times the 508.5 millimeters mercury, which was the vapor pressure of the pure solvent, the pure pentane in this case. You can't really call that solvent per se in this scenario, so it's just the pentane. So we've got 2 sig figs in the mole fraction, 4 sig figs in the pure vapor pressure. I end up with 126.8 millimeters mercury of pentane above the solution. Since we're only good at 2 significant figures, that's going to round up to 130. It's closer to 130 than 120. All right, let's do the same thing for the hexane. It's just going to, the pressure, or in this case, the partial pressure of the hexane above the solution will be the mole fraction of the hexane in the solution times its pure vapor pressure, which provided for you, right? So the mole fraction we calculated for the hexane was 0.7506, good to 2 sig figs. And the pure vapor pressure provided for you in the problem was 149.1 millimeters mercury. That's good to 4 sig figs, so when I multiply, I'm limited by the 2 sig figs. So I get 111.9 millimeters mercury, which is closer to 110 than 120, so that rounds to 110 millimeters mercury. All right, we'll be using the non-rounded values later for part B. Now, does this all sort of make sense? These are both non-polar species, so they're, the intermolecular forces are based on London dispersion forces, which are stronger as it gets bigger. Hexane is bigger than pentane, so hexane has stronger London dispersion forces, and it's harder for it to vaporize. So it should have a lower vapor pressure, pure vapor pressure, than the pentane. Does that make sense? Pentane is smaller, has the higher vapor pressure. Okay, that makes total sense. So would it make sense? Well, we can't really say it makes sense that the pressure is higher because it depends on how many moles we have. Remember, the mole fractions aren't equal. It's not 0.5 and 0.5, right? But hopefully it makes sense why those numbers are different. Why is the number for pentane bigger than for hexane for the pure vapor pressure? Because it's smaller and has weaker linear dispersion forces. Woo! Let's get ready for part B. Hopefully you can see these are relatively easy. This is just a pain in the butt because I didn't give you the mole fraction to start with. So if I had done that, this would be a cakewalk on a quiz or exam, right? Right. So we'd have the partial pressure of each species, both A and B, pentane and hexane, whatever you call A, whatever you call B. The next obvious question is, what's the total pressure above the solution? Right? So you got this mixture of hexane and pentane in the liquid phase. Well, what's the vapor pressure above it? What's the Dalton's law of partial pressure? It's just the contribution of the vapor pressure of the pentane plus the contribution from the hexane. And I'd given you an equation to start with where you could have just done Raoult's law here and here, but since we already calculated those, let's just plug our answers in from part one. So we knew the partial pressure for the pentane above the solution was 126.8 millimeters mercury, good to 2 sig figs. The partial pressure of the hexane was 111.9 millimeters mercury, good to 2 sig figs. But we're adding these together, so we're limited by the largest absolute uncertainty. You can't really go fewest decimal places here because we're out in the tens place. So we're limited to the to the ones place there and the ones place there. See, the ones place is significant, but not the tens place. So we're going to be limited to the ones place in this scenario as far as, the tens, got that backwards. These are the significant figures. Oh, rewind, delete the last 3 seconds from your brain. Let's talk that over again here. So the 1 and the 2 are significant, so we're good to the tens place. The 1 and the 1 are significant here, so that's also good to the tens place. I was reading that backwards for some reason. Too many numbers! So we're going to be limited to the tens place in our final answer. So 126.8 millimeters mercury plus 111.9 millimeters mercury will give you 238.7 millimeters mercury. Limited to the tens place, largest absolute uncertainty. So that will round up to 240 millimeters mercury. That's the total vapor pressure. We can actually plot, in the next video, we're going to plot this in an actual graph. So we can plot Raoult's law based on changing the mole fraction of one species. So start from 0, go to 1, and you can see a straight line for how Raoult's law is plotted. That vapor pressure would increase as you increase the mole fraction. We could do it for both components and then add them together, and we can actually plot the total vapor pressure as the composition of the solution changes. Oh, we'll do that. This video is getting a little long. We'll do that in the next one. So one more thing I'm going to do, part C. Now that we know the composition of the solution, mole fractions of both hexane and pentane, we know both of their partial pressures above the solution, and we know the total total pressure above the solution. We can use the total pressure and the partial pressures to calculate the mole fractions of both the hexane and the pentane in the vapor phase. And we can compare that to the solution phase and see if are they the same? Are they going to have the same mole fraction of pentane in the solution as in the vapor above it? Or is it going to change? Is it going to go up or down? Think about that. All right, let's think about this here real quick. So part C, what is the composition or the makeup of the vapor phase? And we'll do it in terms of mole fraction. So what's the mole fraction of pentane in the vapor phase above the solution? What's the mole fraction of hexane in the vapor phase above the solution? And think about, is it going to be the same as the solution? Or is it going to be different? Well, take a look at the volatilities of the pentane and the hexane, right? Pentane's smaller. They're both nonpolar. So the pentane's more volatile, right? So it more easily goes into the gas phase. So would that make sense to you that the vapor phase would be enriched in the more volatile component, in this case, the pentane? There's going to be a higher mole fraction of pentane in the vapor phase and a lower mole fraction of hexane in the vapor phase than you would see in the solution itself. And we already know the mole fractions in the solution, right? So the mole fraction of pentane in the vapor should be less than that in the solution, and the mole fraction, higher. Because it's more volatile. So the pentane should go up. The mole fraction of pentane should go up, and the mole fraction of hexane should go down going from solution to the vapor because of the different volatilities. The problem is, if we want the mole fraction in the vapor phase, we need the moles in the vapor phase and the total moles. Don't necessarily have those, but we do know the pressures, and fortunately, those are proportional. Yay! So we can use this and just say, well, the mole fraction of pentane will be the partial pressure of pentane in the vapor divided by the total pressure, which we did, right? We got the vapor pressure of pentane in part 1. We got the total pressure in part 2. Just divide those. It's the same as the mole fraction. Isn't that nice potatoes there? Same thing with the pentane. Although technically we don't need to do that. We could just subtract it from 1, right? So we can just calculate from this, subtract it from 1 to get this one, or you could do the ratio. It's up to you. Go ahead and do that. See what you guys get. Track your uncertainty. Did you get them? Did you get them? Let's get the mole fraction of pentane first. You could have done hexane first. Doesn't matter. So the partial pressure from part 1 was 126.8 millimeters mercury. That's the pressure in the vapor phase of pentane above the solution. Divide that by the total pressure above the solution, 238.7. Both are good to 2 significant figures. I'm dividing, so my answer is good to 2 sig figs. So I get a mole fraction of 0.5312, which rounds to 0.53 to 2 sig figs. And that is the mole fraction of the pentane in the vapor phase. Now remember, what was that in the solution? It was 0.25, right? The rounded value was 0.25 in solution. So you had less pentane in the solution, but it almost doubled, right, in the gas phase. So about a fourth of the solution was pentane, and a little over half of the vapor is pentane, because the pentane is more volatile than the hexane, so it enriches in the vapor. Okay? The hexane, you could do the same thing. You could divide it, or just subtract it from 1 because we only got 2 components. So take 1, exactly 1, minus the mole fraction in the vapor phase of 0.5312 of the pentane, and you end up with 0.4688, rounding up to 0.47 to 2 sig figs. So you get 2 decimal places here. That's exactly, you get 2 decimal places or 2 sig figs in that scenario. They happen to be one and the same. But remember, in the solution, hexane was 0.75. So the solution was 3/4 hexane, but a little bit less than half in the vapor's hexane because it's less volatile. We can actually use this to our advantage in a process called fractional distillation. If you go into organic chemistry, we can use the fact that the vapor is enriched in the more volatile component. You could take that vapor, condense it to a liquid, and now you've got these new mole fractions, and then vaporize it again, enrich it even more in the pentane, right? Collect that vapor, condense it, and now it's even a higher mole fraction of pentane. And you can keep doing that over and over and over until you've got mostly just the more volatile component left in the final condensed solution. Maybe I'll show a plot of that, maybe not, depends. But this one got a little long, but it has all the calculations. The next one, we're going to do a logical extension. We're going to plot this. It's a pretty crazy plot called a tie line, where you could do this whole problem I just showed you in about 5 seconds. You're going to like that one. You guys are awesome.